My name is James Titcumb. I work at a place called Rove, and we only have one elephant at the moment, before you ask. But we are making more. It takes a while to make these things. I've been doing PHP since around 2002, programming before that. I'm a Zen certified engineer now, whatever that means, and I'm a contributor to many open source projects. I did try and make a pull request to Doctrine last night, but it got rejected. I am in the Zen Framework community review team as well, and I did actually do some merging last night for once, which is good. But anyway, enough about me. Let's talk about how PHP works, because we need to kind of have a look under the hood and figure out what's going on so we can understand what an abstract syntax tree is. And that's the point of this talk, right? That's why you're all here, hopefully. Otherwise, you're in the wrong room. So anyway, hopefully we've seen something like this, or we have a vague understanding of what's going on when we run PHP. So the PHP code is fed into a Lexer, which generates tokens. The tokens are fed into a parser, which results in an AST, and the AST is compiled by the compiler to generate opcodes. The opcodes are put in the op cache and then executed in a virtual machine. Virtual machine is not Vagrant or anything like that. It's a virtual CPU that executes these opcodes. It's pretty much just some C codes that's written and does stuff, right? AST is new in PHP 7 and above. So that's why I found this quite interesting. I wrote this talk as a result of writing a library called PHP Reflection, which we'll have a look at briefly at the end. So the Lexer is the first step of this process. We're going a bit more detailed, don't worry. I may have lost some of you already, but it's okay. The Lexer is a generated program. So we use a tool called re2c, which takes a syntax definition, which is in this file zenlanguagescanner.l. This file describes how the tokens are split out. So your source code is just a big string, and we need to try and make sense of this string. So we look through and we match tokens, and that's great. And this is roughly what it looks like. The syntax is kind of similar if you've ever seen something called Flex, which is Fast Lexical Analyzer, which is kind of similar to re2c, and is in fact used by HHVM if you ever used that. So a few simple examples here. These are very simple. Lexer is a state machine, so basically it shifts states each time you can change the state and so on, and representative of what context we're in, right? ST in scripting, as the name might suggest, it means we're in normal scripting mode, okay? There are others like ST double quotes, here doc, now doc, and so on. And then the next part is the token itself. These are just string literals, so it will match exactly things like exit, die, function, and so on. Inside the curly braces is what happens if those tokens are matched. So if we encounter one of these tokens, in these cases, all we're going to do is return the token directly. So that basically what that means is that token gets added to this thing called the token stack, or token stream rather, which is then given to the next step. We'll have another look at it. Look at another example. So the states are obviously different here. We're assuming here that we're in double quotes or back ticks or here doc. And if we encounter $curly brace, then we're going to change the state, or YY push state is the function that we call, and we're going to change the state to looking for var name, or var name, depending on how you like pronouncing that. And we're going to return the token afterwards, so $, open curly braces, all right? And this one is will only match if we're in this state looking for var name. And the label there is just a shorthand for matching a variable name, basically, followed by a curly brace. And then if we encounter this, we're going to do this copy value, which basically says, along with the token, we're going to put the lower value, which is the value we match, the variable name. And then we will also change the state back into the previous state we're in, and return the token. All right. Cool. And that's roughly how the Lexer works. So it gets passed, that definition gets passed into re2c, and that generates a C file. You can generate that yourself, and it will look like a really massive C file full of nonsense that will be basically unreadable. But it's generated code. We don't need to know that, but that's part of the steps. The next part is the parser. The parser actually works in kind of a similar way. It's a state machine, but we're trying to add a bit more context about where our tokens are. So all we've done is we've split the string up into tokens. I mean, you can achieve that with just a regular expression, really, but maybe that's a bit more efficient. We'll see. But the parser tries to make sense of these tokens and put them into kind of order, if you like. This is a parser definition. So let Zend language parser.y. This looks a bit more complicated because it is. But real languages are complicated, right? They have you have loads of different ways you can write the same thing. And we have to try and understand meaning and context and make sense of the code, the tokens that we've been given. So we're trying to understand the main parts at least. These are the labels, so this is like the function name, if you like, or whatever. I've not added the definitions for expression and statement onto this slide because it would be so tiny and unreadable, it's useless. But we know what an expression and statement are, right? So we'll look at the if statement first. This will match if we find an if statement without else on its own. Before we go on, this %prec t no else basically says we are left associative, which if you know what that means, that's fine. If you don't know what that means, it doesn't matter. Or we can match an if statement without else followed by an else token followed by a statement. And obviously, as I said, the definition of a statement is elsewhere and it's pretty massive. But to find out what an if statement without else is, we need to look at its definition. And that is, if we get a t-if followed by a literal open parenthesis followed by whatever the definition of an expression is, followed by another literal close parenthesis followed by a statement. Or it can be if statement without else followed by the else if token followed by an open parenthesis, blah, 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 blah. All right? But you can see basically what this does is it tries to match tokens in a particular order. Right? It's kind of a really easy, basic way of looking at it. Let's try and look at this another way, because maybe this is a bit confusing. We'll use these rules to parse this if else block. And the first one will match if statement without else. We get just the if token, we get the open parentheses, we've got an expression, close parentheses, and a statement. We've got another match. We also match the same rule there, because we have the same kind of structure. The if statement without else, i.e. the one that's contained within A, followed by an else if token, followed by parenthesis, expression, parenthesis, statement. Sounds really long-winded, but it's really fast when we're doing this. And finally, the last one matches the if statement rule, because we have an if statement without else, followed by the else token, followed by the statement. Okay. So going back to the definitions quickly, this stuff in the curly braces is also what happens when we match this particular grammar. And there's something important to note here. These things of what to do when we match these grammars, they're calling these functions like Zend ast create list and Zend ast create and so on. That's kind of where we're getting to, right? If we look back at PHP 5.6, it looks very different. We have this function call to Zend do if cond. We like shortening names in PHP apparently. And this will do a load of stuff, basically creating opcodes there and then, right in that the part of the process where the parser is executing. So we're doing something different now. The AST is new in PHP 7, as I said. And going back to the first diagram, the result of the parser is now an AST instead of the opcodes directly, which is good. All right? So the AST is fed to the compiler. That then translates these to opcodes. The opcodes are then executed in the virtual machine. Lovely jubbly. Lost any of you yet? All right. I'm going to simplify things down a little bit more. firstly, what is an AST, right? I haven't really mentioned that, what it is. So far, it's been a bit of an abstract concept. Come on. AST is just a data structure. It represents some code. Funnily enough, it's not actually specific to PHP. This is a general sort of compiler concept which PHP has now picked up on. It's a data structure, which means it can be modified. Thus, you modify the behavior of the code potentially. It also contains metadata like the line number, column number, and file number, and whatever. And we can also do this process called unparsing, which is a fancy word for generating code from an AST. One thing to note is that when you unparse or generate the code, whatever you want to call it, the layout may change. It may not look exactly the same as the code you put in. Because although we have some metadata, not all of it is there. And not all of it is interesting to this data structure, so we don't care about it. Which means when you print it out, you may not have the same format of code. Maybe that's what you want. You could write a coding standards enforcer by creating an AST and then printing out the code, and it will always be consistent then. Maybe. Okay. I think we know what this does. Very simple script, and we're going to produce an AST for this. It's going to look something like this. It's got an echo statement. It's got a scalar string with the value of hello world. Fairly straightforward. Let's get a bit more complicated. A simple concatenation. There's a bit more going on here, though. If we look at the AST representation, we've got an echo and we've got concatenation, which is a binary operator. It's got a left and a right side. The left side is a scalar string with the value hello, and the right side is a scalar string with a value of world. So let's do some mathematics. Let's do a bit more. We'll assign some variables. A is 5, B is 3. We'll do a sum. And already the AST is getting rather big for this fairly straightforward code. Obviously, we've got the assignments, the name of the variable, which is $A for the first one, and then the value is the next part. We do another assign. And we've got this add operation. And you can see actually the right hand side of the add operation is a nested multiply operation. So we actually got this same kind of binary operator, but nested inside it. It's like a tree. But why? Why is this important? Why does this help us? This is kind of nice inside PHP internals because we have decoupled the compiler from the parser now. They are separate things now, which makes things a bit more maintainable. And if anyone has tried to look at the source code of PHP, you can very easily get lost quite quickly. So anything to help that kind of readability is always nice. And it slightly simplifies some of the productions in the parser as well, so that's made that actual step slightly simpler and better, and we've actually fixed a couple of really minor bugs, but that's cool. It's also faster. Now I need to quantify this a little bit because everyone's like, oh, everything's faster. But AST introduces an extra step, right? So you'd think that would be slower. But despite this extra step, no, it is slightly faster. But what I mean by faster is the compilation step is faster, which only happens once, because once we've compiled it, we put it into the op cache, don't we? The runtime performance may be very slightly faster, maybe slower in places. So actual runtime performance doesn't really matter. The actual performance improvements in PHP 7 around zvals and things like that make one of the things that make the big differences in PHP 7 and why it's a lot faster. So the AST is kind of under the hood thing, right? Might not be relevant, but we'll have a look at why it could be relevant. So the AST implementation makes the compilation 10 to 15% faster, apparently. But it requires more memory. But that's okay, because the new efficient zval structure offsets that by lots. All right, so we don't really mind. But the reason why it's faster is because creating this tree structure is a really, really efficient way of doing things. It's really efficient. You can traverse through the nodes and so on, and it makes it quite a fast process. It's quite easy to statically collapse constant nodes as well. I mean, if we have a look at this AST, well, these values are always constant. They're never going to change. There's no actual user input here, so we could actually collapse that down to a single node and say, well, it's just 7, I think, is the result there. But yeah. So this is what exactly the same AST, but represented as a bit more of a tree-looking thing. When we put this up like this, something interesting can happen. If we follow the line all the way around the outside and going in at the little bits and so on, then we get kind of some kind of pseudocode. So if we go through and kind of touch all of these nodes as we go down, then this process is called a pre-order traversal. Some fancy words, right? But if we write them down as we go around, this is what we come up with. And it's kind of like pseudocode, right? Cool. All right, fair enough. The important thing here is that the operation, so assign and things like that, is prefixed, and that's why it's called a pre-order traversal. And the arguments, or the operands, as they're called in this world, come after. And this is called Polish notation. And it allows us to very easily see something important, which is called order of precedence. When writing a programming language, order of precedence is very important. For example, when you have the sum 1 plus 2 times 3, putting away all our maths knowledge, we don't know the answer necessarily. We have to know which of these, which of the sums to do first. Is it 7 or is it 9? If we write it out with Polish notation, the result becomes obvious. We know that the add operator takes 2 operands. We have the operator first, and we have the left operand and then the right operand. The right operand is another operation. So we can descend into that, and we have our operator first, we have our left operand and our right operand, and we can then evaluate that. And we know now the order of precedence. So multiply is higher, if you couldn't guess that. So if we add the sums together, we know that the answer is indeed 7. There's also another way of writing this, which is called reverse Polish notation. It's kind of similar, but it's the other way around. But in order to pass the values here, we build a stack. The values come first, and the operand operates on however many items it needs in the stack. So both of these are binary operators, so they'll take 2 things off of the stack. To build a reverse Polish notation stack from our AST, we need to visit all the leaf nodes first, so the lowest points in the tree, and then come back up the graph, adding the operation nodes. And this is known as a post-order traversal, funnily enough. So maybe let's try and visualize this a bit, okay? We're going to step through each item, and if it's an operator, we'll execute. Otherwise, we'll push stuff to the stack. So what that means is all the values we'll put onto the stack. The operations will take stuff off the stack, basically. So to start off with, we've got values. We're going to add the values to the stack. So we've got all the values on the stack. And then the fourth item is an operator. We've got the multiply operator. So we need to take off 2 items off the stack, because we know that it needs 2 things. Perform the operation and put the result back onto the stack. Cool, okay, we've got a 6. Same thing with the next operator. We're going to do the add operator. We're going to take the last 2 items off the stack, or pop them off, if you like, and add them together and put them back onto the stack. And we've reached the end of our input. Cool. The final result here is that we have a single item in the stack. If you end up with more than 1 item on the stack, something is broken. So, armed with this very dangerous knowledge, we can now write a very simple compiler. We'll write it in PHP, since this is a PHP talk and we're at a PHP conference. But don't do this in production. PHP already does a good job of this. So. There is some source code available. I encourage you to go to my GitHub on github.com/asgrim and find the compiler project there. But first of all, we need to define our language. We're going to have very few things in our language. We're going to really restrict it to make it much simpler, because as soon as you start introducing lots of complex things, it becomes a very complex process, like a real programming language. So we're going to have just very basic sums, add, subtract, multiply, divide, and we can have an integer and some white space. We're going to use positive integers as inputs. We're not going to allow negatives. We're going to allow white space, but we're going to ignore it because it's unimportant in our language. And we're also only going to support one line of input. And also, I'm going to say there's no way to override the order of precedence, so no way to put a brackets and say, if I execute this first and so on, because that gets a bit more complicated, and there's only so much time I can fit into this talk. So I'll simplify it. First up, we need to write a Lexer. This is surprisingly easy. I mentioned earlier, we can do this with regular expressions. So we define all the regular expressions. Note that all of them use the anchor to start the string, that's the circumflex, to assert that we're at the start of the string so that we don't go matching tokens off further down, because we want to go through bit by bit. So this is the code that, this is half of the code for our Lexer. Basically what we're going to do, we're going to analyze from the offset each time and run through all the regular expressions. Each time we match something, we'll move the offset along by the length of the lexeme. The lexeme is just a fancy term for what got matched by the regular expression. And the matching method is very straightforward. We're looping over those regular expressions, trying to apply each one. If they match, we've found our token, so we create a token object and put in the lexeme, that is the thing that we matched. All right, that was easy. We've written a Lexer. You can optimize that a bit more. You could put all the regular expressions into one regular expression, but I wanted it to be a bit readable. But yes, that's the Lexer done. Let's move into parsing. As I mentioned, order of precedence is kind of important. We're going to fix our order of precedence like so. We're going to have multiply being the highest, so it has the highest number, and subtract has the lowest. That's kind of normal maths rules, okay? So we're familiar with that. I'm not doing any surprises here. But of course, in implementing your language, you can change the order of precedence, make things a bit confusing, if you're not already confused. So the order, we're going to order the tokens by operator precedence first, right? So we're going to loop over the tokens. We're going to have two stacks. We're going to have our eventual output stack, and we're going to have a temporary operator stack as well. We're going to have a look at how we deal with operators, because obviously that's what we're interested in. And the code in there looks like this. There's a bit of stuff going on here. We'll go through bit by bit. Basically, we're going to add the token to the operators stack, and then continue through it. However, on each iteration, what we need to do is we need to loop from the bottom of the operator stack and work our way backwards and find out if the last item on the stack has anything with a higher precedence. If it does, we pop it from the operator stack and we push it onto the output stack. Okay. Finally, any operators that are left, at the end of that function, we'll pop them all onto the pop them off the operator stack and onto the output stack. And then we'll return the output stack. Basically, what we've done is we've just reordered all those tokens. We can have a look at how it does this, because I've got another fancy diagram. So first token goes straight onto the output stack, because it's just a value. The next is an add. So we're going to put that in the operator stack. When we do that check, we make sure there's nothing of a higher precedence. There isn't. It's empty so far. The next is just a value, so we'll push that onto the output stack as well. We've got the multiply operator. We'll check the stack and see if the last item is of higher precedence. It's not, so we'll just add the multiply operator onto this stack. The next is a value, so we can put that straight onto the output stack. And then the last step was to take all the operators and put them onto the output stack. Look familiar? That's our reverse Polish notation. Cool. All right, that's how we did that. So we now have to create an AST for this. So we have a stack of tokens, it's in the right order, that's good. We can use a very simple stack compiler pattern. So we progress through the stack using a loop. The IP is the instruction pointer, that's kind of useful if you want to give some useful feedback about parsing errors and things like that. If it's a value, we're just going to create this new integer AST node. The node structure should have any metadata that's relevant. In this case, the relevant metadata is the token that we matched, i.e. the number, right? If it's an operator, we're going to pop the last two items off of the stack, just like we showed, and push them onto the, we're going to create an operator node. There's some code I omitted which figures out what kind of operator it is, whether it's plus, minus, subtract, or divide, and figures out the class name for it. The full code, as I mentioned, is on GitHub if you are worried about how this works. It does work, though. And we end up with this AST, and it looks like this. And we have all the nodes we expect, which is great. So then we have to execute. This is actually the easy part. Maybe the same level as the Lexer, I don't know. We're going to create a tiny virtual machine. So I mentioned that word earlier, and basically that means we're going through and executing stuff. It's just a fancy word. There's some specifics about it, but we're not executing code directly on the CPU is the point. So we're going to descend through our abstract syntax tree and run it. And this is our compiler function. There's only two functions to our compiler because it's a very simple language. You don't need too much. If it's a binary operator, I'm going to call another function. And if it's an integer value, we're going to just return the actual value. We don't have any other nodes, so that's it so far. The binary operator node compilation function looks a bit like this. So when we come into this function, we don't know what the left and the right values are. We need to compile them first. So we recursively go through and descend through these nodes by using the compile node function again. So we looping back round, right? So they could be other binary operators, or they could just be an integer. We don't know. So we call compile node, and then that will give us the result of that, that node, the value of that node that we want. So when we've compiled the left and right, we just figure out what kind of operation we need to do, and this is where we do our real magic. We've got our plus, minus, times, and divide. Okay, so we've written a compiler. That would hopefully work if you check that out on GitHub and Composer install and so on. And you'll be able to see that and play around with it. And it's kind of fun. Now, I know what you're thinking. On the surface, this doesn't seem really relevant to my day-to-day work. Well, I mean, it is kind of relevant, right? We've got faster, more efficient code. We've got some scope for future optimization as well, as I said, like constant node collapsing and other ways of like looking at parts of the tree and optimizing inefficiencies away. We don't do very much at the moment in PHP, but there is potential. And knowing how the engine works can be really beneficial. As I mentioned, AST isn't really specific to PHP, so in theory, like the first time I looked at ASTs, I was like, oh look, we can translate some PHP to JavaScript or something, or the other way around. In practice, that doesn't really work, because all languages have their own quirks. Even really good languages have quirks. But hopefully this helps you understand how these standard languages work. It's the same kind of process for all of them, really. But we can use ASTs in userland. Why would we want to do that? This is so we can get really good insights into our code. We can have a look at what's going on. We can examine the structure of the code, and we can do some magic things, which we'll look at in a bit. There's an extension called php-ast. It's not part of core, unfortunately. This extension was written by Nikita Popov, and it's only available for PHP 7 up, because PHP 5 didn't have an AST. But it exposes the AST to userland, so you can see what's going on. The downside is it requires an extension, and extensions can be a pain to set up, depending on your environment. But this is what a use case would look like, right? Once you've installed the extension, you call the AST parse code function, and give it some code. The AST dump function here is just a helper function to display the AST nicer, because if you look at AST, it's enormous, it's huge, really big. So this kind of simplifies the output so it's a bit more readable, for us mere mortals. There's another extension called astkit. This is an interesting one. It's written by Sarah Goldman, and it actually allows you to modify the AST as well. Ooh. And then you can execute it. So you get this effect called monkey patching, which is pretty cool. The downsides are that it's an extension, and it's not very stable, and it's probably never going to be worked on again. I had confirmation from Sarah, so it's just a toy to play around with, okay? Does anyone use RunKit in production? I did have someone in a talk last week that put their hand up, and I told them off. Nicely, of course. This is an example of the astkit. We load up the AST for the code in very much the same way, but then we can modify stuff. And we can see here that when we execute it the first time, we're going to get the result we expect. And then we can do this thing called a graft operation, which is change what the node is. Instead of being a true, we're going to change that to a false, and then we'll see that the cake is a lie the second time we execute that, of course. So there's also this other library called PHP Parser. Now I said a moment ago that you can't get NST for PHP 5 code. Well, that's not true. Because you can use this library called PHP Parser. It's again written by Nikita Popov, and it's a very useful library. It's more or less the same, it fulfills the same purpose as the PHP AST extension, but it's written in PHP. Yes, indeed, it's a PHP parser written in PHP. The upsides are, it's not an extension, so you can install it with Composer and it just works, all right? The downside is that it's order of magnitude slower. Like, this is really, really slow compared to doing anything natively, which is a trade-off, right? Oh, there we go. It's alive. Okay. The usage is pretty much exactly the same as well. We can configure it to prefer PHP 7 or indeed prefer PHP 5 if you're still using PHP 5 code. You give it a string of code, it gives you your ST. No surprises. And I'm going to do a bit of shameless self-promotion here, but it's okay because it's open source. I'm not trying to sell you anything. Better Reflection is a library that me and Marco Pavetta wrote, and it's all about using the AST generated by PHP Parser to create the Reflection API. And it works. It's very flexible, quite powerful, and it allows monkey patching. And we'll see how. So this is a very rough overview of how Better Reflection works. The reflector is kind of like the public API, so we say, oh, create the reflection and so on. The source locator is you giving it instructions on how to find code, because you can load code lots of different ways. We give the code to PHP Parser, as you may expect, and then we return the reflection itself, and the reflection just looks through the nodes of the AST we've generated. The core reflection API looks like this. We've tried to keep Better Reflection as close as possible. Of course, as the name suggests, we hope that it works both with core reflection as well. So you give it the name of the class, very straightforward. Better Reflection is the same, except you call this static constructor called createFromName. Under the hood of this is where it starts to get interesting. So first of all, we actually call this other static function called buildDefaultReflector. These are basically default rules on how to locate source, which look like this. So we have a PHP internal source locator for classes and functions and so on that are internal to PHP, so built in, basically. We have eval source locator as well, if you like eval in code. Well, we've got to support it, right? And then autoload source locator, which is, as the name suggests, it crunches the autoloader and does some magic wizardry to figure out what class we're trying to load so that we can reflect on it without actually loading the class. because if anyone has ever used RunKit, then you'll know that that is the extension that you use to unload classes from PHP memory, because as soon as it's in memory, you can't unload it by default. So when we want to reflect stuff, we don't actually want to load the class, which is kind of the big difference between core reflection, is that you have to have it loaded, right? It operates directly on the class entries in PHP. So yeah, when we call reflect, all we're doing is just invoking the PHP Parser once we've figured out where the source code is located. So if you're given a class structure like this, pretty straightforward, we can get an AST that looks something like this. So much in the same way as the statements and additions and so on we had earlier, we also get the information about the classes, the functions and methods and so on. So we get all of the nodes, and there's loads of them. But there's only a certain number of ones that we are interested in for better reflection, because we're trying to find out about code structure. So we have the class nodes, and it has an array of statements. It has a property node, which has a type, a name, and some attributes and so on. We have a method node, which has a type, parameters, a load of statements, which we've kind of looked at, and some attributes as well. And then the class itself also has attributes like start and end line and so on. So what can I use better reflection for? Everything you use normal reflection for. Well, mostly anyway. But the big difference, as I kind of alluded to, it means that you can now reflect on classes in files and strings and so on without actually loading that into PHP. We don't use the internal reflection API at all, so there's no reliance on there. But it's nice because you can actually analyze doc blocks as well, and we get type information from that using the PHP documenter libraries. It's slightly less relevant now we've got PHP 7 because we can do type declarations directly in PHP 7. And there's a nice potential for static analysis here. If you're not sure what static analysis is, it's basically, as the name suggests, statically analyzing. That is, not running the code, but looking at what what types and things that lie around. Better reflection can also modify stuff. So I mentioned monkey patching. Let's have a look. You've got a class called myClass, and we've got a function called foo. It returns 5. Very simple. So we're going to reflect on the class. I'm going to use this special source locator because I just want to load a single file. And we create a reflection from it. Make sure you do this before it's loaded because, as I mentioned, PHP can't unload classes. We have this thing called a class loader as well. And we have this method of storing the reflected the result of this operation because it's slow. We know it's using PHP Parser and so on. This must be done after all the other autoloaders like Composer and so on are registered, which if you're using it like this, it probably will be anyway. And now we use this method, setBody from closure. Also exists setBody from string, setBody from AST, so you could parse it a load of PHP Parser format AST nodes. And as the example suggests, we're overriding the actual body of that function with our own function. So then when we execute it, it will return 4 instead of 5. Ooh, that's kind of fun. I don't recommend you do this in production, but you could potentially use this in like a pre-deployment step. So you could remove some type hints, for example, and what I mean by that is every time you enter a function in PHP that has type declarations, there is a very small amount of checking that goes on. Yes, we have to guard the types, right? So depending on the mode you have, if you have strict types on, it will throw an exception if you put in an invalid type. If you don't have strict types on, then it will try and cast that value to it, and if it can't cast the value, it will then throw an exception or error. If I remember rightly. So every time you enter a function, it has this little cost. But what we can do is, on a class's public API, we can leave the type declarations in, because they're important. But once the values are inside your class's private API, we actually don't need them anymore, because we've already written the code with certain expectations. Now, as long as you're not using stuff that's from global or outside the scope or anything like that, then this will actually work quite nicely, and any private method that gets called will have that cost removed if you remove the type hints beforehand, for example. I keep meaning to write a library that does that to demonstrate what I mean, but I haven't got around to it yet. I have life and so on. So for the PHP engine itself, it means better decoupling, and we're always striving to decouple things, right? The AST is a really efficient data structure that we can go through really, really quickly, and it's an efficient compilation process. Yes, it's faster in some respects, but what I mean by that is faster in compilation, ignoring the op cache and so on. But the userland concepts are what really interests me. As I mentioned, the PHP Parser library, better reflection, which allows you to reflect on not yet loaded files and do monkey patching and dangerous things like that in userland code. But probably the best application for all of this stuff is static analysis. And trying to detect bugs before your deployments. So there's this tool called execat, which uses its own AST structure, but it will allow you to do this static analysis. And there's also a tool called FAN, P-H-A-N, not F-A-N. That uses PHP-ast extension, but that will allow you to do static analysis as well, which is nice. And that also catches issues with code coming from PHP 5 to PHP 7 as well. So it will make sure you're forward compatible if you haven't yet migrated to the latest and greatest PHPs. And this kind of stuff you will put into your continuous integration workflow and so on. So you run it along with your unit tests and so on, and you run these static analysis tools, and it will say, oh, you've written some terrible code, and you should be ashamed of yourself. And I write terrible code. We all do, right? We just see how much terrible code we can get away with. All right. And on that note, cheery one, are there any questions? Don't be shy, it's okay. I have a question here. Yeah.
You said that PHP Reflect, the PHP Parser is a magnitude slower than the extension.
Mm-hmm.
Well, better reflection, is it able to swap out those implementations?
Okay, so the question, if you couldn't hear it, is the PHP Parser implementation is much, much slower than the PHP-ast extension because it's written in userland. And is better reflection able to swap out those implementations? The answer is, at the moment, no, but it's something I'd really like to do. The reason I haven't dropped it yet is because there's still a load of PHP 5.6 support going on. And, as soon as everyone's moved over to PHP 7, or at least the majority of people have moved over, that's something we can certainly look at. The reason why it's so difficult is because the objects that represent the trees are so different. You'd think they'd be the same, but they're not. They're slightly different. But it's a bit of reworking to introduce the PHP-ast extension. And of course, the other downside that makes me not want to do it is you have to install an extension. So that's the other stumbling block. But I believe at some point in the future, when, I don't know, the PHP-ast extension will become part of core. At that point, yeah, there's a no-brainer. We'll migrate over. And then that'll be really fast, and then you can do monkey patching in production, maybe. I don't recommend this, by the way. Okay. Any more questions? I think I have time for maybe one more. No? Okay. Well, I want some lunch, right? I'm hungry too. So thank you very much, everyone. Please leave feedback.